Let us derive a relation between the thermodynamic variables pressure, volume and temperature for an adiabatic process. Adiabatic process is a process where the heat exchange between the system and the surroundings is not allowed. That is, neither the heat enters the system nor the heat leaves the system. Thus, the change in heat content of the system is zero, or the heat content of the system is constant. For such a process, we will derive a relation involving these variables pressure, volume and temperature. To begin with, again, we start our discussion with the statement of first law, which says that dq is du plus dw. For adiabatic process, we have already said that dq is 0. This simply implies that du is minus of dw. Or du plus pdv is 0 because dw is simply pdv. Now we will use the definitions derived while discussing Mayer's relation. We have seen that du is ncv dt. So this equation 2 becomes ncv dt plus pdv is equal to 0. If we apply Mayer's relation, which says that Cp minus Cv is equal to R, which also gives us Cv is equal to Cp minus R, here we get Cp minus R times dt plus Pdv is equal to 0. Now if we separate these two terms, we get Ncp dt minus nRdt plus Pdv is equal to 0. Further, if we see that since Pv is equal to nRT for an ideal gas, we get, if we differentiate this, differentiating this gives us first into derivative of second plus second into derivative of first. UV rule of differentiation applied on the left hand side is equal to n and r are constants, so they remain as they are, into dt. So if we look at equation 3 and this particular equation, we see that this term shifted on the left hand side gives us minus nRdt plus pdv to be equal to this shifted on the right hand side gives us minus vdp. So for here we get this expression minus vdp. So we write it as ncp dt minus vdp is equal to 0. Further, we have already written somewhere here that, or in the previous derivation, that ncp dt is, okay, let us do it the other way. So we can rearrange this to get ncp dt is equal to vdp. So this is our first equation, call it as equation A. And we have already seen that ncv dt, which is du, which is minus of dw for this particular process, since dq is 0, So which is also equal to minus PdV. Correct? This is by definition of du. This is valid for adiabatic process and this is again by definition. So we get NCV dt is equal to minus PdV. Now this is our second important equation. Now we are going to divide equations A and B. We are going to take ratio. So divide equation A by equation B. We get NCP dt upon NCV dt is equal to VdP by minus PdV. So N gets cancelled out, dt gets cancelled out, and we are left with Cp upon Cv is equal to minus V by dV into dP by P. Now as we have already seen in the previous video, this ratio Cp by Cv is a constant. It is denoted by letter gamma. So we get gamma is equal to minus V dV into dP by P. Let us just separate the variables to get dV by V into gamma is equal to minus dP by P. So we have taken these two terms on the left hand side, or gamma dV by V plus dP by P is equal to 0. Now since we have separated the variables, we can integrate this equation easily. Integrating integral gamma dV by V plus integral dP by P is equal to some constant of integration. Let us denote this constant as some k. Now we know that integral of 1 by x dx is log x. So applying this formula here, we get gamma into log V plus log P is equal to C, or let us say it as k. Now by the rule of logarithm, gamma log V is log of V raised to gamma plus log of P as it is. Now let us replace this constant by any suitable constant and write it as log of k. This is what we do while taking integrations and in order to simplify the mathematics further. Since k is a constant, log k is also a constant, so they both can be equivalent. So again, by the rule of logarithm, log a plus log b is log a into b. So we have log of p into v raised to gamma is equal to log of k. Now we can eliminate the logarithm from both the sides and we get an expression pv raised to gamma is equal to constant. This is a very important relation between P and V for an adiabatic process. So this is a relation which involves P and V. So if we eliminate one of these variables, we can introduce the other variable T. So let us try to do that. Since the gas is assumed to be ideal for this case, we have PV is equal to nRT. So this P is just nRT by V. So use this instead of P here to get nRT by V into V raised to gamma is equal to constant. So we get T V raised to gamma by V is equal to constant divided by N upon R. Note that N and R are constants. So this entire term is also a constant. And this gives us T into V raised to gamma minus 1 is equal to constant. So this is the alternate form of the same relation which I already derived, which involves the two variables temperature and volume. Similarly, we can rearrange the terms and with the help of these two equations, we can get a relation between temperature and pressure as well. We can easily prove that T raised to gamma, P raised to 1 minus gamma is equal to constant. So these three relations are very important when we are going to deal with adiabatic process. Thank you.